Welcome to the weekly LLMs Research Podcast. This week we dove into ICLR 2026 accepted papers and found 14 papers that address problems you'll hit when building multi-agent systems.
All the classic problems.
Every single one. Slow pipelines, expensive token bills, cascading errors, brittle topologies, and of course, the classic, I have no idea what my agents are saying to each other.
So we've grouped all that into 5 key problems.
And we'll walk through what the research actually proposes to fix them.
It's a huge collection this year, and honestly, it's really timely. Because usually when we talk about multi-agent systems or MAS, we're seeing these, flashy social media demos.
Oh, absolutely. The kind where someone on X claims they spun up a team of agents and wrote a sci-fi novel in 5 minutes.
Yeah.
It looks like magic.
It does.
Until you actually try to deploy it in a real enterprise environment. I was working on an RK pipeline just last week, and we tried to add a second critic agent to verify citations. The whole system just slowed to a crawl.
Yeah, the reality hits fast.
Immediately. It's slow, it burns through API credits like you wouldn't believe, and half the time the agents get stuck in this polite loop, just complimenting each other.
The infinite politeness loop, I've seen that. That's exactly why we filtered the ICLR 2026 acceptances specifically for engineering relevance.
Right.
We're not looking at the theoretical what-if papers today. We're looking at solutions to the bottlenecks that actually break production systems.
Okay, so where are we starting?
We're going from latency, why it's so slow, all the way to the black box problem of just understanding what they're even doing.
Perfect. So let's unpack that first major headache, which is exactly what I hit last week. Speed, or, the lack of it.
A sequential bottleneck.
It's a killer. If I have Agent A doing research, passing it to Agent B to draft, and Agent C to critique, I'm just waiting in line. If I have 4 agents, my latency just quadrupled.
And for a user-facing app, that's a complete non-starter. It is. And there's a paper that tackles this by borrowing a concept from CPU architecture. It's called speculative actions, a lossless framework for faster AI agents.
Speculative? Okay, that immediately makes me think of speculative decoding and LLM inference. Is it the same kind of intuition?
Precisely. Think about how a CPU uses branch prediction. It doesn't wait to know for sure which way the code will go. It guesses.
And if it guesses right, it saves time. If it's wrong, it just discards the work.
Exactly. This paper applies that same logic to agent actions.
Okay, but with a CPU, we're talking nanoseconds. With agents, we're talking about full API calls. How does that work in practice?
So your typical setup has a massive intelligent leader model, say GPT-4 or Claude 3.5, deciding the next step.
Which is slow.
Very slow. This framework uses a smaller, much faster draft model to predict the likely next actions. Then it executes those API calls in parallel based on the guesses.
So you're firing off multiple potential futures at once, based on a cheaper model's intuition.
You got it. And the paper calls it lossless because the big model still comes in and verifies the final result. You aren't sacrificing accuracy for speed.
So if the little model was wrong, the big model just says, nope, and you toss that result.
Right. But in their tests on things like web search and OS control, they hit up to a 30% speed up.
That's significant. I mean, 30% is often the difference between a user waiting and a user just closing the tab.
It really is.
But speed isn't just about individual execution. Sometimes the system is slow because there are just too many cooks in the kitchen.
And that brings us to a paper called Graph of Agents. This one directly challenges that idea that more agents is always better.
Which is the default assumption, isn't it? If I have a hard problem, I just throw a coder agent, a reviewer agent, a security agent,
and a manager agent to manage them all. You end up with the noisy cocktail party problem. Everyone is broadcasting to everyone.
Okay, so what does Graph of Agents do?
It uses something they call node sampling. They look at model cards, which are basically summaries of what each agent is good at, and they dynamically select only the relevant ones for that specific prompt.
So it's a filter. It's checking credentials before letting an agent into the room.
A really harsh filter. In their benchmarks, GoA actually beat a baseline that was using 6 agents by only using 3 selected agents.
Wow. So less noise really does mean a better signal.
And faster execution. By cutting the graph down to the essentials, you get better answers and you get them quicker.
All right, so we can make our systems faster by speculating on actions and by, firing fewer agents. But that leads right to the second problem, the one that usually gets the CFO's attention.
Ah, yes. My token bills are out of control.
Exactly.
The coordination is powerful, but that coordination costs money. If you have agents chatting back and forth in English to agree on a plan, you are just burning through tokens.
And English is so verbose. It's a terrible data transfer protocol for machines. We're taking these clean mathematical concepts, translating them into paragraphs, and then asking another machine to turn them back into math.
That is the exact premise of a paper called KVCOM. They basically ask, why are we forcing models to translate their internal understanding into English just so another model can translate it back?
Okay, so what do they send instead?
They share key value pairs, the KV cache, directly.
Direct tensor injection. That feels invasive. For anyone listening who might not be deep in the weeds, the KV cache is essentially the model's working memory of the conversation, right?
Exactly. It's the mathematical representation of the context, the vectors. So instead of generating text, Agent A just takes the tensors representing its thought process and pipes them directly into Agent B.
But isn't that a massive amount of data? I mean, full model states are huge.
You'd think so. But they found you only need to share about 30% of the layer's KV pairs to get near upper bound performance.
And upper bound is?
They define it as if the models were literally merged into one giant brain.
That is wild. So we're just skipping the natural language bottleneck completely. But there's a catch, right? I can only do that if I have access to the model weights.
Correct. This is strictly for open weights, your llamas, your mistrals.
So if I'm stuck with closed APIs from OpenAI or Anthropic, I need a different strategy.
You do, and for that, you'd look at a paper called PCE, or Planner Composer Evaluator. This one tackles the inefficiency of just having a long chat log.
Right, because usually we just append the entire conversation history. Agent A said this, then Agent B said that, and it just gets huge.
And it's unstructured. PCE converts all those latent assumptions into a structured decision tree.
A decision tree. That sounds surprisingly old school.
It's classic AI meeting modern LLMs. Instead of a long, winding conversation, the system builds a tree where the internal nodes are assumptions and the leaf nodes are actions.
And it scores the different paths.
It scores them based on cost and likelihood. So it plans the logic before acting, instead of figuring it out through expensive trial and error chatter.
That makes a lot of sense. Structure prevents drift. But speaking of things getting huge, there's another cost sink. The context window itself. Just appending history until you hit the limit or the bill explodes.
The infinite scroll problem, there's a solution proposed for this called MEMM1. It's a reinforcement learning framework designed specifically to maintain a constant context size.
Constant. So it never grows, no matter how long the agents run for.
It doesn't grow. It forces the model to consolidate its memory. It basically uses RL to teach the agent to strategically discard redundant information while keeping the important stuff.
So the reward in the RL model is based on whether it can still solve the task after it deletes information.
That's it. If it deletes something important and then fails the task, it gets penalized. If it deletes noise and succeeds, it gets rewarded.
And the results.
They saw a 3.7x memory reduction, and this is the really cool part, a 3.5x performance boost on long horizon tasks.
Because the model isn't distracted by junk context.
Precisely. It turns out hoarding tokens isn't just expensive, it actually confuses the model. A cleaner context leads to sharper reasoning.
That's a perfect segue to problem 3. One agent hallucinates, the whole pipeline fails. The fragility issue.
The cascading error problem.
Yeah, if Agent A hallucinates a single fact, Agent B treats it as gospel, and by the time you get to Agent C, you're completely off the rails.
There's a fascinating paper on this called When Does Divide and Conquer Work? That really breaks this down mathematically. They decompose failure into 3 types: task noise, model noise, and aggregator noise.
Okay, let's unpack model noise. What's the key insight there?
The aha moment is about how model noise behaves relative to the context length. They found that model noise grows superlinearly with context length.
Superlinearly, so doubling the context more than doubles the noise.
Yes. And this explains something many of us have seen but couldn't really prove. A weaker model that uses a chunk and aggregate strategy can actually outperform a giant model like GPT-4o that's trying to process everything in one shot.
Because the giant model, even though it's smarter, is just drowning in that superlinear noise curve.
It's drowning. The divide and conquer approach manages the noise better, even if the individual brains processing the chunks are smaller.
That's a huge takeaway for architecture design. Don't just rely on that million token context window, split the task, but, errors will still happen. And when they do, my current debugging strategy is basically stare at the logs and guess.
You and everyone else. But log analysis only gives you a hypothesis. I think Agent A failed here. It doesn't prove anything.
So what's the alternative?
That's where the Dover paper comes in. It stands for Intervention-Driven Auto-Debugging.
Intervention sounds active.
It is. Dover doesn't just read the logs. It actively goes in and edits the history. It'll alter a plan or change a message from a past turn to see if that fixes the final outcome.
So it's A/B testing the past. It goes back and says, okay, what if Agent A had said this instead?
Basically, yeah. It simulates different paths from the point of failure. And the results are impressive. This method allows developers to flip 18 to 28% of failed trials into successes.
Because it pinpoints the exact intervention that was needed.
Exactly. It tells you what to fix, not just where the fire started.
That's so much more useful than a stack trace. Okay, let's move on to problem 4, which is topology. My agent graph breaks when I swap a model.
This is the hidden fragility of static graphs. You hard code that the summarizer talks to the translator.
Right.
Then you upgrade the summarizer to a new model, and suddenly it stops following instructions or the format changes, and the whole connection to the translator just breaks.
We need dynamic plumbing.
We do. One solution is called Card Conditional Agentic Graph Designer. It proposes that the graph structure itself shouldn't be fixed. It should be generated based on the environment.
So if I swap in a dumber model, Card might automatically add a reviewer node to compensate for that.
That's the idea, yes. It adapts the topology to the resources you have available. But there's an even more extreme version of this called MAS squared.
Yes. They argue that the whole generate once and deploy mentality is just flawed from the start.
Yeah.
They use a generator implementer rectifier team.
So the system is recursively generating its own agent structure to fit the problem.
Robots building robots, effectively. And it works. They showed a 19.6% performance gain. But what's really interesting is the cross-backbone generalization.
Meaning?
If you swap the underlying LLM, say, you move from Llama to Mistral, the system just re-architects itself to work with the new brains.
That's the dream, right? You don't have to rewrite your whole agent setup every time a new model drops.
It's getting closer.
But is there a way to do this without a manager agent explicitly building the structure? Can't they just organize themselves?
They can. That's from the stochastic self-organization paper. It's a decentralized approach. Agents generate answers and then assess their peers' contributions using an approximation of Shapley values. Shapley values. That's from game theory, isn't it? It's a way of assigning credit to players in a cooperative game.
Exactly. It measures how much did this specific agent actually contribute to the final correct answer. A directed acyclic graph DAG just emerges naturally based on that.
So information starts flowing from the high contribution agents to the others.
The hierarchy emerges from competence. You don't design it. And this is crucial for weaker LLMs that need that structure to function, but can't be trusted to design it explicitly.
Okay, so we've covered speed, cost, errors, and structure. That leaves the final and maybe most unsettling problem. Problem 5. I have no idea what my agents are saying to each other.
The black box. This ties right back to what we discussed with KVCOM. If agents are sharing tensors, humans are completely locked out. But even if they're just using shorthand, they can drift into their own language and we lose oversight.
So how do we keep it human readable without losing all that efficiency?
One attempt is GLC grounding language and contrastive learning. They really acknowledge that trade-off. Symbols are fast, words are slow but understandable.
So what's their fix?
GLC uses an autoencoder to create compressed symbols for the agents, but, and here's the trick, it forces those symbols to align with human concepts using contrastive learning.
Contrastive learning. That's basically pushing similar things closer together and different things further apart in the vector space, right?
Exactly. So they force the vector for the compressed symbol to be mathematically close to the vector for the English explanation. You get the speed of symbols, but you can still map it back to something a human can audit.
Which is vital for compliance. If my banking agents deny a loan, I need to know why, even if they used compressed vectors to decide.
For sure. But beyond just the language, how do we even know they are actually collaborating? That's the focus of the emergent coordination paper, they ask. Are the agents collaborating, or is it just spurious temporal coupling?
Spurious temporal coupling. I love that phrase. It means, did they solve it together, or did they just all happen to solve it at the same time by themselves?
That's it. They used information theoretic metrics to measure this, and they found something that sounds obvious but is often ignored. Simple prompts are not enough.
You have to be more explicit.
To get real collective intelligence, you have to assign specific personas and explicitly tell the agents to think about what others might do.
You have to prompt for theory of mind.
Yes. Without that instruction, they're just individuals shouting in a room. With it, they become a team.
And speaking of theory of mind, there's one last paper that takes a very different angle on this. Rote.
Modeling others' minds as code. This one is a personal favorite. It argues that we shouldn't model agent behavior as abstract beliefs or desires.
We should model it as
Executable code.
because social interactions follow scripts. Wait for green light, then walk.
Exactly. If customer is angry, apologize. These are just programs. Rote treats theory of mind as a program synthesis problem. It tries to reverse engineer the code the other agent is running.
That makes so much sense. LLMs are trained on code. They understand logic flow better than abstract feelings.
It improved prediction accuracy by 50%. It turns out treating minds as software is a pretty effective way to predict what software will do.
Okay, we have covered a lot of ground here. Let's do a quick recap, sort of a toolkit for people listening.
Sure. If you need speed, you should look at speculative actions for parallel execution. Remember, use a draft model to guess ahead.
And graph of agents to filter out the noise with model cards.
Right. If you need to cut costs, check out KVCom to stop paying for English translation and pipe tensors directly.
And MM1 to use RL to stop hoarding all that context.
Yep. If you're drowning in errors, remember that model noise is super linear. Use the insights from when does divide and conquer work to split your tasks, and use Dover to actively debug by editing the history.
And for a brittle topology.
Look at MASS for self-generating structures that adapt to new models.
And finally, if you need to understand what's happening,
check out RoteTE and GLC to ground those compressed communications back into human concepts.
that is a solid arsenal for 2026. But what's missing? What's the next big problem?
There's always something. While we have these great fixes for speed and topology, the papers this year are still a bit light on a long-term stability.
Like over weeks or months of operation.
Exactly. And adversarial robustness. If a bad actor injects a poison prompt into one agent, how does the whole graph protect itself? I think those are the big questions we'll be looking for answers to at ICLR 2027.
Well, plenty to keep us busy until then.
Absolutely.
Thanks for listening to today's podcast. If you like what you heard, subscribe to the LLM's research newsletter and podcast for free. We cover research that matters for practitioners every week. See you next time.